Hello, everyone, and welcome to our afternoon session. Well, afternoon in the Eastern time in the United States, at least. This is the Responding to COVID-19 track. So great to see everybody. I hope you all enjoyed your regional sessions. I know that they were, the ones that I had the chance to see were really, really remarkable and had some really fantastic conversations happening. So thank you all for your participation there. And we are all here to kick off the Responding to COVID-19 track with a very special session featuring Just One Giant Lab and JOGL. So this is going to be a epic 110 minutes of JOGL madness that we're about to get into, which I'm really, really excited about. And I want to just kick things off by introducing Thomas Landrain, who is going to be the host for this session. And I just want to say, you know, Thomas, obviously, excuse me one second, there's a screen popping up. I've been following this JOGL journey with you for a number of years now, and I think this is a really important point just for everybody. You know, it feels like just in the past number of months, of course, the work that's been happening on JOGL has scaled so dramatically, and there's been so much activity. But all of this has been years in the making, like years and years of hard work. I mean, I remember, you know, Thomas, you were coming to Cambridge like every bunch of months with Mark and Leo, and just like for years. You've been working on this, and Thomas has been presenting about JOGL at BioSummit for at least 2 years. And this is the third year that Thomas is presenting on JOGL. So I think this is one of those things where people like see something happening and it's like, oh, great, like it just happened and it was so great. But no, it actually requires a huge amount of work over a very long period of time. And then when the conditions are right, something very nonlinear can happen, like what happened, you know, when COVID-19 hit. So I just wanted to say, you know, it's just been amazing to see all of the hard work, Thomas, that you and the team have put in over these years. And then watching you kind of in real time grapple with all of these challenges all at once, and just seeing how amazing the work has been and how rapidly you all were able to grow and adjust to these challenges and just handle this whole situation so marvelously. So with that, I just really want to thank you for being here, Thomas, and to all of the JOGLers that are here. And I'm personally so excited to see all of the talks and all the great work that you've been up to. And so with that, join me in welcoming some snaps and some claps and some love for Thomas Landrain.
Thank you so much, everyone. I cannot be more happy to, you know, it's the first time basically that we're presenting, you know, JOGL Open COVID-19 as a group, you know, with the community, with the makers within this community, publicly. You know, we've been giving presentations there and there, but it was pieces. This is the first time that we're making like a whole session about what's been going on the biotech side of Open COVID-19. So I'm really excited actually to see the kind of content that will be emerging out of those discussions. I'm going to start with a short introduction about JOGL and Open COVID-19. Then we will have 15 minutes of talks directly by the makers of the members of this community. And then we have a 15 minutes session of roundtable where we have, you know, we'll be able to get deeper into the understanding of what made this collaboration possible and what does it mean for the future, you know, of this community and of science in general. So what I'm going to do is actually I'm going to share my own screen. So I don't. Could you remove? Actually, I don't know who shared the screen first, but.
Thomas, should I stop this, or I thought like you know,
yeah,
I'm sharing it
yes.
and then okay.
Yes, thanks. So I'm going to share first a small presentation I've made and couldn't copy paste it in Google Slides. So this is going to be better. So this is really like a short introduction. We are a big community, and this community is really a big example of, you know, a big trend. What's going on? It's not only us. It's been going on, you know, for like forever. I mean, this is probably one of the most human thing to do, to get together and try actually to solve problems together. But with digital technologies, it's been changing, and we are facing global problems now. And so it's not about only solving local problems. It's really about how do we get together, you know, with a higher critical mass in order to be able to crack those complex problems. Because, you know, it's not only about biology, it's usually about economics, social aspects, planets, it's chemistry, it's engineering. It's hard actually to have just a small team of people locally that to have the right context and the right means to crack a problem. Being able to have this collective intelligence appear, emerge, out of those digital networks is really a big given. And so being able to play with this and support those kind of collaborations is really marvelous for science in general, for the advancement of science. And I'm going to say why just now. And so, open laboratories have been around for quite some time. We have this huge network of Fab Labs, biohackerspace, and that's fantastic. But biohackerspace are mostly focused on local community. How do we bring all those people together? That's really the question. And so, I've been myself driving also open laboratories in France, based in Paris, with La Paillasse, and it's been fantastic. But I always had in the back of my mind, like, how do we spark more global collaboration? Yeah, as David said in the introduction, it's been really in the work for many years through La Paillasse and through JOGL with Mark and Leo. And what's fantastic is the communities have this aspect that they give the opportunity to non-professional to get involved. And this is really what matters here, because we have public institutions that somehow well framed, for professionals that really wants to get their whole life, to put their whole life into a subject, or if you want to create a company and if you follow a good principle of a business model, is going to be successful. But again, there are so many problems out there in the world that doesn't fit in those two worlds, especially problems where you don't have any business model because nobody can pay for the solution, or because the problem is not fit for academic career. So, or it's just that you get disconnected, from the field. So that's where communities really gets in, and it gives the opportunity for anyone to stand up and say, I want to be able to work on this problem because this is affecting me. And I don't care if I don't have a PhD or whatever. It's like, I'm going to build a community of people that can help me achieve what I feel is right for the community. And so being able to support this is really important. And it's hard because so far, not that much actually institution, we could say actually non-institution are really made for sustaining and supporting those kind of community approaches. We have amazing organizations such as the Global BioSummit. And it's great, but we have all those biohackerspace, and it's great too. But none, are somehow made to support projects. It's great to spark collaboration, but how do you actually bring those communities? How do you bring them to work together on the long run? So this is really was the frustration I had of the many years I spent within that community, which is fantastic. But like, how do we go further? And so the point is, how do we go beyond the few millions of current contributors to science? We have about, I calculated using numbers from the UN, like we have about 8 million researchers in the world contributing to, academic knowledge, like, published knowledge. How do we get there, that to time 10, like 80 million? We have to recover people that are not in academia anymore, but got higher education and could contribute. So we have actually to build a different thing. What's the main aspect here? How do we make this happen? By solving an accessibility issue. We have so many people that have an idea about how they want to solve a problem. They could be researchers, could be entrepreneurs, could be civil servants, could be activists, could be, anyone basically. We call them leaders. And then on the other hand, you have many people who cannot actually get access to the right framework. They don't know really what's going on, and they would. However, they would like to help. They would like to contribute. But they don't know where to start. And so really, on one hand, you have all those leaders, but they usually lack resources. It can take up to 2 years from the moment you have an idea to the moment you can make a proof of concept. It's a long time, and there is no reason why it couldn't be shorter. And especially if you can give the opportunity to a lot of volunteers, to get in on board and work with you on this, especially if it's a common interest problem, something that is going to benefit to the whole society. So that's the reason why we built just one giant lab. And so the way it works, it's a virtual platform. It's not a physical space. The idea is it needs to be distributed. You need to be able to get onboarded from wherever you are, and you get to connect with others, build teams, work on projects, document what you do, share your needs, and so we try to have this social network aspect. But not only the idea is to not only be a network, but also be an organization that can support projects. And so that's what we do is we build research programs, and that's what we've done with to answer the pandemic. Basically, we've built the Open COVID-19 initiative, and it's been taking quite some time to really understand how to make this happen. And we're going to discuss all that matters in the roundtable afterwards. But what's amazing is Open COVID-19 has been kind of a call for projects, and we had so many people answering, and you're going to hear people that have answered that call and build projects together in the next few minutes. And so what's important is it started around diagnostics, but it's what's interesting is it didn't end there. It's like so many people joined in that they wanted to work on not on diagnostic, but on prevention technologies, on treatments, on just basic understanding of the pandemic. And so we built this framework where they could organize themselves. And so currently we have more than 100 active projects around COVID. It's really quite amazing to see, and it's still growing. I really encourage you actually to check the projects, or even actually, if you're not on JOGL yet, to bring a project there. It's a fantastic digital community that has been very involved in every aspect of the program. And it's been really at the core of Open COVID-19 and the way JOGL functions. And David was speaking of how this pandemic has been really a spark for us. Because we've been around since July 2019, and the pandemic has been the moment where, like, the use case where we could really prove the usefulness of such an approach. And here you see the boom, in terms of users and projects after the pandemic started. And in fact, this is a small animation of what's going on in the world, like where our users come from, and so I think it's very beautiful to see. We're not. You can clearly see that most users come from developed countries, and also quite a lot of people coming from India. This is something that we are truly working on, and trying to make the platform as accessible as possible. It's already accessible in many languages, and so it's at the end, the point is, how do we connect, not a few thousand people, but how do we connect a few millions, or even a few dozens of millions of people? So I don't know how many minutes I have right now. Am I late already? But
we're over time according to Anish.
Okay. So we're going to talk about it in the next session with the roundtable. What are the advantages of community-based community-based approach? And truly, it's like being able to share the burden, of managing a community in all these aspects, because it's so massive. You have so many people. So being able to distribute those aspects have been really, really important. So monitoring, reviewing, onboarding. We're going to talk more about that. And especially regarding reviewing, what has been instrumental in this program is the fact that we could convince our partners to fund us so that we could fund the community. But, basically, convincing that this community is able to do as well, if not better, than a normal academic laboratory, because the level of collective intelligence is much higher. We have much more skilled, experienced people coming together, being able to build really neat projects. The thing they lack is, however, that because they're so new, it's such a new team, people that never met before, that it's very hard for them to go and apply for some funding and wait for 3 months, 4 months minimum, before getting an answer or being funded. And a community, a new team, what really matters is the momentum. So you have to keep the momentum going. And so we've put in place what we call the macro grant system, where the time between the moment the project applies and the moment the project receives the grant, it's less than a month, basically. We try actually to make this happen, and so that the momentum can be kept. And we've done 3 rounds. Actually, we just announced the 4th round so far. We've been funding more than, I think, 25 teams so far for more than 60,000 euros. The way it works is micro grants that are up to 5,000 euros. I think that's a model that we want really to pursue, like to convince more and more actors to go through JOGL to be able to fund such a beautiful community that is completely invisible to institutions because we don't click any normal lines in their system. So being able to be this interface is really important. And in fact, those are our main partners so far. The AXA Research Fund has been fantastic, super supportive, and the Agence Française de Développement, and the APHP, the Paris hospitals. And so I want to, okay, I don't want to take too many minutes out of speakers. So what's been really impressive, what we've seen is, because JOGL is purely online, it has a planetary reach, meaning that you're doing something automatically, you're being, you gain visibility basically to almost any place in the world. So if someone from Nepal wants to be able to work on something that is related to your project, there is no reason why that person won't be able to contact you and collaborate with you. And so that's really beautiful. And so I'm going to finish by just thanking our partners, because none of this would have been possible. It's been a very long journey. People had to make the same bet as us, saying, okay, is this going to work? It is feasible. And so we want to thank them. And obviously, I want to thank also our team. I'm so fortunate that we've been able to create such an incredible team of people. A team has grown during the pandemic, because we were half that size in February. And so the need that appears during the pandemic, they made us actually, we couldn't face it. No, we couldn't face it with our current size. So we had to recruit massively, and we found actually most of our new recruits within the community, people that were already helping JOGL voluntarily, and say, okay, man, you're great. I do want to join us full time. And so that's been really a great experience. So I'm going to finish here, and thank you for your attention. And now is going to be the next part, the best part. We're going to hear about the projects that are actually making this whole operation fruitful, have an impact. And we're going to hear from 6 projects. We're going to let me actually stop sharing that screen and go to there.
Tomas, really quickly, as you're setting this up, just in terms of time, so Anish was looking at the total block, but for your individual speakers, because I think Ara, if you were keeping track of the individual speaker time, that would be valuable, because you're only going to have the whole session has to end at 4:20 p.m. Eastern time, so you guys can just make sure that you're distributing the time well.
Perfect.
Great.
Thank you, David. So let's, can you go to slide 6, please, Aravinth? Perfect. So the one before. Yeah. So we're going to start with diagnostic teams. We have 4 projects, and I have to say, I've been so impressed by the quality of the work they've been doing. We're not talking about 4 projects as 4 projects in what you would find normally in a normal, let's say, hackathon or innovation competition, those are 4 projects that are fully cooperative. And it's kind of like a giant team, and they're exploring the problem of diagnostics in a similar but also complementary way. So I will start first by calling Ellen Jorgensen for the 1-hour COVID test, and then we'll follow with the other ones. Ellen, are you here?
Yes, I am, and I'm ready to start my little stopwatch on my phone to try and keep to time. So go ahead and go to the next slide. We just wanted to celebrate the fact that the 4 teams that are presenting right now, that's not the first slide, it's the one with the X Prize thing. We found way after we started this that the X Prize was running this cheap, fast COVID test, and all of us entered, and amazingly, the 4 teams you're going to hear are all in the semifinal round, which means that we're going to get actual samples from the X Prize to test, and they're going to give us feedback, and there's a chance to make it into the next round where they start actually giving us large amounts of money. So I think that the only thing that I would say about this is it's an external validation of exactly what Tomas is talking about, that our projects have been validated by an external source, and I think that that's really amazing. Next slide. So JOGL has facilitated our success in a lot of different ways. I mean, first of all, you just heard from Tomas, anyone can create a project, ask for resources, recruit members. It facilitates cross-disciplinary, cross-background, cross-geography collaboration. And the micro grants, I think, are a really key part of this. Next slide. So the interface is really easy to use. You see the arrow up in the upper right, you would just join JOGL. Next slide. And this is what a project page looks like. Next slide, which you can create, or you can join a project. That's just scrolling down in the project page. And this is, there's just an incredible buffet of projects already there. You can see just in the COVID-19 diagnostic and detection, there are 27 active projects, 566 participants. So the door is open, and we encourage everyone to join this exciting effort. Okay, I will talk now about our specific test. We called it the 1-hour COVID test because we don't have a lot of imagination in our group, I'm afraid. And it seemed like the right thing to do. Next slide. Our particular team is sort of a microcosm of what JOGL is all about. We happen to have scientific backgrounds. We all have started community labs in different places. We're all totally passionate about accessibility to biotech. We live thousands of miles apart. We've actually never met in person. And our lives and labs are very different. I mean, we sort of represent mid-career, late career, early career scientists. We're all just very, very different. But because we're part of this larger JOGL diagnostics community, we found each other. Next slide. So where to start? There were a lot of people talking about a lot of different things in the beginning of this pandemic. There were all sorts of methodologies that were starting to be published, thrown up as preprints. We started out trying to validate a particular type of test, but what we wanted was something with minimal equipment, with reagents that weren't going scarce, like the RNA extraction kits, something you could do with relatively little training, low cost, and of course, safety and quality. And I think the thing that was nice about JOGL is we had 3 different lab situations. Mine is a home lab. My company, Annika Biosciences, very graciously let me work on this. Sarah's in BioBlaze, which is a community biolab, and Chris Monaco is at the CDC. Next slide. So there are 2 different paths you can take with isothermal amplification. The reason we chose isothermal amplification is it hits all the things of easy to use, easy to do, very little equipment. You really just need something that will heat either water or a heat block to 65, around 65 degrees Celsius. That's it. And it's a one tube reaction. It's very simple. And the two types of outputs can be either colorimetric, which includes, there's also one that's turbidity based, or fluorescence. And there were people working on fluorescence, and we decided to explore the colorimetric. Next slide. Mainly because of this publication from New England Biolabs, where they had used their colorimetric lamp master mix to do some detection of SARS-CoV from patient samples. And the first thing we started out was trying to validate that approach. Next slide. We very quickly realized that the pain point in all of this was the RNA extraction step. The reason that you want to extract RNA from the samples is that two reasons. The first is that the RNA is not that easy to get out of the virus. You have to treat it with either heat or chemicals to get it out in order to analyze it. And the second thing is, during the extraction step, you often concentrate it. And then also the downstream technology may not work very well with a crude sample. So that was where we ended up focusing massive effort. Next slide. So beware of preprints. We tried everything. Mainly poor Sarah, because Sarah had the only BSL-2 space. And so she was working with inactivated virus, and a lot of that extraction, you can do all you want with the twist naked RNAs and things like that, but the rubber hits the road when you're starting to use something that's an actual viral type sample. So we tried a lot of things, and a lot of preprints, which sounded really great, didn't work all that well at all, or were really tricky. Next slide. So we ended up with a test that actually is not very DIY. And one of the reasons is that Sarah's actually in the process of getting epiLAB status for her space, and wants to actually do the test in the Chicago area. And so we ended up using a commercially available mouth swab from Genotech. And it's a nice design because the cap comes off, you turn the tube around, you put the swab right into the tube at the buffer and activates it, so it's very, very safe. There's a reagent called PrepIt, sold by the same company, that does some weird magic, which they don't reveal, but the RNA actually kind of ends up at the top of the tube without any centrifugation, so there's no equipment needed except a pipetter. And you pull it off, dilute it a little, and it goes straight into the isothermal master mix reaction, which, as you can see from this, turns from pink to yellow if the sample is positive. Next slide. So what's next, and I'll be really fast because I've already run over by a minute, is that obviously we want to make this more DIY. We want to do some engineering to see if we can't reproduce the things that we're buying commercially right now. The Open Enzymes group, which you'll hear for, is doing really exciting things. I would also say that when benchtop DNA synthesis becomes a reality, that will help with the primers. And it's interesting because this opens the whole door to how far can we really go in self-testing. And I think that that's something that we'll throw out for the discussion later. I think that's the last slide, maybe one more. Nope. All right, take it away, CoronaDetective.
Who wants to start, Guy?
Yeah, I'm gonna start, I guess. Right. Cool. So our project is CoronaDetective. We've been all working together this whole time, and we use a slightly different methodology. And this was inspired by, I've been working in this isothermal space for a few years now. It started from the Zika and dengue epidemic in Brazil. But we've been doing, and I gave workshops at the last two BioSummits on this GMO detective. So we've been really working on trying to get this as simple as possible so people can do. So you take a little piece of food you want to test, you do some kind of simple DNA extraction, You transfer that to the tubes, you heat it for 1 temperature, and then you can, again, see the reaction with your eyes. Next slide. So isothermal amplification has some advantages over PCR. I mean, because it's usually a lot quicker, like this takes half an hour to an hour, and not, a lot of times the PCR takes 2-3 hours. It's very sensitive and specific, and you only need 1 temperature. But the primer design is a bit more complicated, and it's also more complicated to multiplex. Next slide. The way we do detection is we use a method called QUASR, which is quenching of unincorporated signal amplification reporters. And LAMP can sometimes have some false positives because these enzymes really like to copy stuff. So this kind of lets us, helps us with that. And you can also do multiplexing. You can do with you can do different colors for different targets in the same tube. Next slide. Looks really bad. And then we do so the way I usually do the isothermal heating is with one of these commercial sous vide machines, which cost $50. And then you can do thousands of reactions at the same time. When open PCR or even these cheap, or can only do like 1 strip at a time or something like that. And I think, Rachel, it's your turn.
The really great thing about doing these open science things based around the GMO detective is that Guy had already really planned out a really super detector system that's really cheap. It costs less than $2. Little kids in workshops solder it all together and get to see their reactions work. So it's easy to build and use. And the different fluorophores show up really nicely. So you can see in this panel B here, there's the first tube is sort of the negative control, and then there's the positive showing that the extraction of the plant material worked well. And then in the second round, the second 4 tubes of this set of 8, there's the negative control for the GMO, and then the positive control, and then the 2 tubes with the that were negative for the food ingredient without any GMO. And so what we really wanted to do was make a multiplex reaction so we could not only get 2 unknown samples per set of 8 tubes, but actually get 5 unknown samples per unknown tube. So using the viral target for the N gene, which is at the very far end of the coronaviral genome, labeled with the green FAM, and using our internal RNA control for the extraction control, using this RNase-P labeled with hex, it makes a sort of slightly more orange color, and the FAM makes a greener color, and they really work together as a nice multiplex, which might show on the next slide. But just to mention first that also we can have other colors. So we want to have ultimately a triplex where we could even maybe test for influenza at the same time as we test for corona, because this might be very important as flu season comes to America and the Northern Hemisphere. The great thing is that Guy has all the infrastructure for doing the lyophilization of these tubes. So the reaction tubes actually should be shippable anywhere in the world without any cold chain dependence. And so and they can also be frozen down in different formats. So the 8 tube strips were used usually for the GMO detective, but for CoronaDetective, we're thinking we can also do 96 well plates, and that will help us readily scale things up. And once the freeze-dried tubes with all the reactions are sent wherever the tests are going to be run, all you need is the buffer liquid and the sample. And within a half hour, you could have your result if you're positive or negative for coronavirus, and know that your extraction was good for the this tricky sample preparation stage, which will really be happy in X Prize that it will give us a chance to test all this. And of course, the idea is that it's going to be affordable to anyone, anywhere. While it costs about $2 per test at the small scale, including the preparation and the consumables, when we do this at scale in large volumes, each tube could cost less than $1. And the idea, and we've already made protocols for this, we have protocols for both the users and for actually making the tubes. So local manufacture and testing of thousands of samples per day could be done for less than the cost of some used qPCR machine. And testings of thousands a day could be done with a very minimal investment. And so then our long-term goal of CoronaDetective is really to avoid the need for commercial enzymes. Right now we're using the beautiful NEB enzymes, and of course we have to buy primers and nucleotides, but ultimately several members of our team, and you'll hear more about this soon, are working on the open source enzymes, especially Kathrin, and ultimately we hope that all these in silico strategies and also using some of the free gene possibilities and things from Fernan will make this even more open source. And ultimately, for the sampling, we have in our protocol, for the user protocol, we basically left it a bit open. We said there were different options for different contexts. First, you could have a quick and easy sort of saliva sampling where you would be really screening for people with high titer virus, or a relatively simple method to concentrate the samples for really high sensitivity and no UC, just a single virion particle. And we're really grateful to this whole JOGL initiative for making all this happen. And I think it's Ali next, right? So there's more. The other thing, there. So somehow these.
Sorry, I have to refresh because there were some alignment issues. I hope it's better now. Yeah.
That's much better. Thank you very much. So the really good thing is that this method is very sensitive. Tell me if I'm late on time. So we can get down to 20 RNA copies with a synthetic RNA, which means 1 copy per microliter of reaction. And this primer set that we're using has already been FDA approved for an early use authorization. And on the next, so yeah, I could just show you, here's water gives the negative sample, then the 20 and the 200 showed up very brightly. And then the swabs, our environmental swabs are all negative. And then here's the multiplex. So here, the first 2 tubes are the water, the next 2 have 200 copies of their RNA in the reaction, so 10 copies per microliter. Then this is the internal control for the cell RNA and for both RNA. So like I said, there's this sort of slightly oranger color for the internal control with this great QUASR detection. And
or it could be red, it could be a different color too.
Exactly, so we're hoping we'll add the 3rd color like red for the flu viral primer set for this LAMP reaction. And I think it's really, the great thing of course is that it's all open source and collaborative, and we really have brought in different teams working together, and we already have people in Sri Lanka, in Cameroon, in Chile who have said, in Ghana, who said they're willing to test and validate our tubes after they've been shipped just in the ordinary mail. And again, all of this is open science. We're pushing, really sharing the results, documenting the experimental stuff, and ideally it will be locally reproducible. The whole team has really been amazing to get to know. And this slide was actually brought together by Aravinth for presentation that he did, so I guess it makes sense that it looks like he's going to be talking next.
Yeah, thank you. I think it's a good segue. So I think it's also a little bit of explaining because we are a little bit of a different organization than the other ones. So I want to tell that, we are a Dream Space Academy based in Sri Lanka. We are trying to solve local challenges, empowering underprivileged youth in war affected region in Sri Lanka. So when I joined JOGL, I really want that technology to be locally reproduced, and for that we don't have that much of technical and infrastructure resource. So I have to look for some partner in the country to bring this and to introduce them to the open science and the JOGL platform so that it can be locally reproduced. So that's that partner is Slintech, is Sri Lanka Institute of Nanotechnology. For them, it's the first time they're doing some kind of an international or decentralized open science, and it has been a great journey to learn. So the huge difference also, we had a little bit of a Blade Runner style name, the CoronaHunter, so that every RNA is lamped. Where, you know, so this is our team. So it's from DreamSpace and Slintech and University of Sri Javathanapura, Professor Neelika, where she has the access to BSL-3 and the clean room where the corona patients have been tested real life in Sri Lanka. So other teams have already explained the fundamental protocol, and there's only a small difference in what we have done based on what we need in Sri Lanka. So what we did, we took the RNA, we took the sample and we did RNA extraction using magnetic beads. This is a little bit of a costly part, but anyway, it's a faster process for us. And then at the end, rather than using a simple fluorometry device, we just used the RT-PCR equipment, which was readily available at the infrastructure. So we were able to quantitatively measure the amplification, and then, you know, everything else in the master mix, and then, you know, everything is the same as the other project. So as you can see that, yeah, we have this threshold, like, you know, the positive and negative. In the real time, we were able to measure the lamp reaction. And then the good part is that we are one of the teams, since we had access to the BSL-3 and also to the center, the university where they have tested. So we actually tested with the clinical real life patient sample, and then this is what you see. Like, you know, we had a pretty good statistics there. And again, like it was explained, and currently our solution with that setup of RT-PCR existing and then RNA extraction using magnetic bead cost around $7 per test, which is still half the price as what is been paid for RT-PCR. And also we have presented this to the Ministry of Healthcare and to deploy this along with the RT-PCR and RT-LAMP at the airport and the main center, so that we could really test the whole setup. So somehow it's an island, Sri Lanka is an island, and we didn't have much cases, and then we have only 13 deaths and around 4,000 plus infection. And so I'm again saying thanks to all the support given by JOGL here, because it's the first time for Sri Lankan institution like Slintech to work on such a collaboration. And then we are happy that we got also shortlisted for as a semi-finalist for the X Prize. And so the next team is going to be Ali.
Can you hear me? Hello.
Yeah.
Yeah.
Yep, we can.
Cool. So I kind of anticipated, since I was the last presenter of our diagnostic efforts, that there would be a lot of detail on LAMP. So I kind of prepared my presentation. There is going to be some detail about what we're doing this differently, but I kind of wanted to give a little bit of a bigger picture of what kind of pushed us to work on this project with JOGL and other groups. So next slide. So for me, there is this question, you know, the diagnostics are happening with a molecular reaction that's been around for a long time. Why, and I'm sorry, just to apologize from the beginning, my presentation is going to be very US centric, just because that's where I'm from, and I'm looking at the situation from where I am based. Why in the US especially have we not been able to mobilize all of the resources we have, grad students, undergrads, labs, thermal cyclers, in the service of testing populations? So in my perspective, it's actually a three-pronged crisis that we're dealing with. One of them is a systematic healthcare crisis. The other one is a crisis of actual molecular biology, the field that we find ourselves working in. And the third one is actually a hyper-individualistic perspective that we find ourselves coming from. Next slide. So to kind of go into it in a little bit more detail, in terms of healthcare and diagnostics, we are strangled by two major monopolies, Quest and LabCorp, which have a stranglehold on the whole diagnostic system, whether that came through mergers and acquisitions, or different kinds of ways where labs are able to actually communicate with hospitals to maintain patient privacy, et cetera. And this kind of led to a very centralized diagnostic landscape, which actually made the system very clumsy. So when a pandemic hit, there wasn't able to be this kind of like nimble reorienting of the labs and the people who can run these diagnostics to deal with the situation. In terms of molecular biology, again, there's a similar situation of consolidation of companies and reagent providers that, unfortunately created these bottlenecks. And, when the pandemic first hit, everybody's talking about shortages of kits, so molecular biology has really kind of become this, how well can you use a kit with buffers that are labeled, buffer A, buffer B, not knowing what goes into them. You can't kind of make them yourself. So I think the way that molecular biology has evolved through these large companies and has prevented us from really understanding what we're doing in the lab. And then, this idea of testing individuals rather than identifying clusters. In the US, I think now it's changing because, push comes to shove, people have to deal with this problem, is that, testing, finding individuals rather than looking at clusters of infection. So pooled sampling was really overlooked. We saw that this was actually a different approach in, places like Germany and Thailand and China and South Korea, where they did implement pooled testing and were able to kind of deal with the pandemic, in a much more efficient way. And, the ultimate kind of example of this is how, the anti-maskers see themselves as fighting for some kind of freedom, free speech. Next slide, please. So the solution that we are proposing is actually to develop the tools that allow for decentralized networks that can conduct self-diagnostics of their communities in a distributed way. So when we're talking about distributed testing, we also have to talk about, kind of allowing for people to have as much, self-sufficiency and self-reliance as possible. So it's not just the distributed testing, but also the distributed production of these tests. So echoing what some of the other presenters have said, being able to produce enzymes locally, rather than, being beholden to the NEB facility in Massachusetts. Reagents, understanding what goes into a reagents, having backup versions. If something is not available, you can use something else. Consumables, instrumentation. There are a lot of questions that need to be solved when you kind of implement a system like this, which is, how do you ensure quality control? How do you do validation? I think we can come up with these solutions by, thinking together. And also this, in my mind, is the only way to really tackle an emergent pandemic. You need this kind of distributed testing system rather than a system where samples are going to labs, takes 2 weeks to identify an individual, if they have it or not. So in terms of what we're working on day to day at the bench, loop-mediated isothermal amplification makes sense. It's an appropriate technique, but also I think it's important that we just don't focus on the means, but also to what ends we're doing this. Next slide, please. So just to kind of go into a little bit of what our project is about. So we build these diagnostic cartridges that are simple and cheap. At the same time, they're robust and sensitive. I'm going to show a little bit of how it works, but I definitely did not prepare a kind of a technical presentation. So we were able to modify some of the existing systems to bring the limit of detection down to 25 copies. We want it to be cheap. We want, this kind of distributed production of the reagents. And one of the things that we bring to the table, which is similar to CoronaDetective with their lyophilization, is that we want it to be able to be stored and shipped at ambient temperature to deal with this issue of, maintaining a cold chain. I think that's a serious problem for decentralized testing. And then, of course, this pandemic will be over, and we should remember that, before COVID-19, there are many regions in the world that deal with infectious disease already. So, they also need to be able to have testing capacity, as well as we should be prepared for the next pandemic. Next slide, please. So I'm running low on time. I'm going to kind of like zip through this. Basically, the central idea is that we use different kinds of low melting temperature waxes to separate the different components of the lamp reaction in order to provide stability, both thermal stability as well as physical stability. And so you can ship them, you can open them from the box, you can use them right away. Same deal that other people presented. You can, we use the QUASR system as well. You can multiplex reactions. You're seeing something with our internal control on the screen. You're seeing co-detection with influenza B. So we have really kind of through the past months, and this is a big team that's working on this, mostly based out of the Oakland Genomics Center in California. We've able to refine our cartridges to be much more reliable and sensitive. Next slide, please. So I just kind of wanted to briefly touch upon how the collaboration with JOGL has really helped our project. One of the great things is just having weekly meetings with the other people that you heard from to bounce off ideas, understand what the challenges are, kind of share the things that we've learned in the past week, and that's been very invaluable for our group. Our projects have been greatly facilitated, whether it's through microgrants, and in our case, we had a huge problem trying to do clinical validation in the United States, despite it being kind of the epicenter of the pandemic. So through our connections with JOGL, we were able to actually conduct validation at a hospital in France, in a research institute at the Pontificia Universidad Católica de Chile in Santiago, Chile. So this has really opened up doors and made us being able to progress. And it's also added people to our teams. Next slide, I think it's the last one. Yeah, so I just kind of want to end here is that I think it's important that we think about not just the tools and that we're building, but also how they can be used. Because, in my mind, when I, for example, first started hearing about these immunity passports, it kind of freaked me out a little bit. So if we're making testing cheaper, quicker, easier, I think it also behooves us to think about to what ends these tests will be used. That's it. Oh, one more slide. Yeah, so I'll just end with that.
Thanks so much, Ali, everyone. I think we have a little video to pump the spirit of this atmosphere. Let's see. Do we have the sound?
1 second. I think I need to then. Yeah.
For reference, this is the video that was used for the XPRIZE application. Yeah. I could get tired of watching it. The next, so we just finished with the diagnostic teams, and again, I really want to thank them for their amazing work. We're going to have, we'll have some more time in the next session with the roundtable for you to ask.
Okay, so I'm going to need to.
Right now, from another project about open enzyme production in the context of producing enzymes usable for diagnostics tests.
Okay.
And so we'll be hearing from Scott and Kathrin.
Yeah, so if I can actually get shared screen, okay. So desktop share, and can somebody call it a time test now? How much time do we have?
If you could do it in, 5 to 7 minutes maximum, that would be great.
Okay. Okay, so I'm going to be doing the beginning bit, and then Kathrin's going to join in on the second bit. So this is our page on the Just One Giant Lab of the COVID-19 project page, and you can get a lot of the details there. So let's see, why is my arrow not, my computer's heating up? Yes, okay. So this is a distributed collaboration. There are 4 groups. There's Team BioBlaze, which is largely Isaac Larkin, who's unfortunately hasn't been able to make it to much of the BioSummit, and Sarah Ware. And so they're working on this collaboration at BioBlaze. Kathrin is based in Germany and part of epiLAB. And I'm here in Vancouver, and then Keany, of course, is part of the Free Genes program. And come on. Okay, so everybody's heard by now about the Open Enzyme Collection, and this is an amazing collection of resources that this community and greater communities can access and use. Jenny Malloy kindly let me use her slide here. So it was designed by Jenny's group with many collaborators. It was synthesized by Free Genes. It's distributed under the OpenMTA, and Jenny's group is funded by the Shuttleworth Foundation and these other organizations. What I want to talk about through this program is, for the Open COVID-19, is a subset of these. And okay, I have to use my cursor to advance it because my arrow. So a few months ago, something happened around the world. And so, of course, everybody is trying to think, how do we take advantage of this? So we had a number of powwows. Some of them actually involved Ginkgo Bioworks, but it was really about trying to build a pathway that we can use the leverage of all the different people working with Free Genes to be able to put out some systems that could help with the initiative. And of course, it all surround, there we go, the COVID-19 diagnostic enzymes. We're focusing of all of the Free Genes enzymes on just 2 classes. That's the reverse transcriptase, which is the enzyme that converts RNA to DNA. And then there are a variety of different polymerases. So for the standard quantitative PCR assay, one uses a TAC polymerase or sometimes other polymerases. And then for the LAMP assay, it's the BST1 polymerase or variants of that. And so these enzymes are in the Free Genes open, the Free Genes open enzyme collection, and anybody can order them. The genes are actually, it's a MoClo strategy, so you have to be able to assemble them into vectors, but this week actually we're receiving the next round, which is actually the components to be able to put together vectors, and so we'll be building quite a few of the the vectors, but we already have them in proprietary backbone vectors like the PET system. So this project's really about three things. One is looking at traditional purification techniques and trying to see how we can extend those or simplify them. The other one is about creating novel fusion proteins that overcome some of the cost problems of the traditional protocol. So with the traditional protocol, one takes an enzyme gene, they put a tag on, for example, the 6 amino acid histidine tag. It binds to nickel columns. So nickel columns are actually really expensive. We're using that as a test bed and a comparatives bed. But then there's also the possibility of fusing other things to these enzymes, for example, purification tags. So like if you have a sand, we might be able to use a silica binding domain that originally evolved in diatoms. And if we take that and fuse it to the enzyme, can we then just use sand to purify the enzymes? Another domain, and this section is a brainchild of Isaac Larkin. If we want to use another domain like a cellulose binding domain, can we use paper to purify the enzymes? And then the third component of this is taking the enzymes and trying to optimize them. So the enzymes that are in free gene are all off patent. Some of the current enzymes that cellars like New England Biolab cells are mutation variants of that. And so this last step, I will actually hand it on to Kathrin to talk about. And I'll advance this, whoops. There you go, Kathrin.
Hi, thanks.
Yeah. You have 2 minutes, Kathrin.
Okay, I will go quickly. Yeah, so I just met the Just One Giant Lab community with the purpose of developing a test, and I saw there already so much test developed, so I switched our purpose in open enzyme optimization. So with the BST wild type, which is off patent, there's a problem that it's not as halotolerant as it is needed for a one-pot solution. So we will do some rational design on it. And we are currently doing relaxation mutation screening in Rosetta Commons on the high performance computer cluster in Darmstadt, and AWS gave us a note for stability assessments and MD simulations. So we will do like a 200 nanosecond simulation of the mutants we screened, and we will also do it in vitro. And there's just for 10 seconds another thing I wanted to add in the next. So in the next slide.
Oops.
Yeah, so I actually started in a hackathon and met the JOGL people afterwards, which was really great. And I still have contacts to a lot of projects there. So we are, so I also have contacts to projects doing open source IT infrastructure for epidemiological follow-up and containment. So if you are somehow interested in this topic, just follow this link. It's actually from the Helmholtz Institute in Germany. So it's also infrastructure that's already rolled out in Ghana, Nigeria, Fiji Island, and actually developed during the Ebola crisis. So yeah, I'm out of time. So yeah, I just stick to that. And thanks for your patience and interest.
Thank you so much. So we're going to have some time again later on to have questions. So we're going to jump right away to Bastian, who is going to talk about his project Quantified Flu, about how he's using data from wearables to predict infections. Bastian? Are you around, Bastian?
Yep, I'm here, sorry. Let me get started and set up the screen share. There we go. Can you see it?
Perfect, yeah, thanks.
Okay, great. So I guess the topic is now for something completely different in good Monty Python fashion, because this one is pretty unrelated to any wet lab biology. And what we've been working on for since end of March, I guess, pretty much, is this idea whether we can use our wearables to see when we are falling sick with any infection, basically, not specifically related to COVID, but of course, the idea came up because of the current pandemic. And oops. The question was really, can we see any of these signals in our data? And it came up during one of our community calls in the Open Humans community, which is a group of pretty nerdy people that like self-tracking in all different kinds of forms, using wearables, using social media, yada, yada. But so coming out of one of those community calls, we wondered whether it's actually possible, and started just people remembering when they were falling sick in the past and plotting some of the physiological data they had collected in the past. And in the top row here, what you can see is basically just the body temperature deviation and the heart rate deviation over time. And you see these spikes here. You can see when people report having fallen sick, and you can see indeed just a bit before people fall sick, there is already some body temperature increase before they are consciously aware that they're falling sick, and the same for the resting heart rate. And of course, we are not the only ones to think about this. So already, this is a blog post from the 14th of March, as you can see, where someone used this Oura ring and said like, oh, I noticed that I was having lots of weird recordings where my body temperature was increased, my readiness score went down. And actually it turned out he had coronavirus already. So this is just in like the N of one background, but of course also there's already a bit of research of this in terms of influenza. There's already studies that have been published some years ago about how you can actually do influenza surveillance on a population scale using wearable mobile health devices. And that's all pretty cool. And we're not the only ones to do this. There's lots of academic research that collaborates with different corporations that make these wearables to publish data out of this. And unfortunately, what this leads to is that there's a lot of hope around it, but even more hype. And people publish stuff like, oh, we can make a 90% accurate anticipation of symptoms 3 days in advance of this. But the question really is, what does this mean for me personally if I'm having such a warning? And also, what does this 90% actually mean? Like, how much of this is false positive if we think that, for example, having any infection at any given moment is pretty rare and we always just predict you're not having a disease? Then we have a pretty good accuracy, but unfortunately, it's completely meaningless. And also it's important that we actually want to know what are potential confounding issues from our everyday life. So maybe it's having gone out to a bar, having had lots of drinks, which drives any changes and so on. And the problem with all of these academic and company-driven efforts is that there's no feedback to participants, the data is not shared at all, and there's no support for the individual in actually learning from their data, because everything has to squeeze through the PR squared, which is both peer review and public relations. And this together means that actually in the short run, nothing will really happen about it. So what we try to do with Quantified Flu pretty much is to say we will not do epidemiology, but rather it's about generating personal insights and learning for the individual participants instead of just feeding into some anonymous machine learning algorithm. Instead, it should be community launched and driven, and individuals can opt in, of course, to make their data publicly available for research, but you can also do it privately just to learn by yourself. And the setup we are doing with Quantified Flu is that we allow people to import data from all of these wearables, be it Fitbit, the Oura Ring, Garmin, Apple Watch, or whatever puts data into Google Fit. You can put it into Quantified Flu, and you can do an ongoing logging of symptoms and say, did I feel sick today, yes or no? And you can actually see your symptoms in relation to your physiological data at any moment you want. And you can do the same retrospective logging of events that we have seen earlier in like the preliminary work. And this ongoing logging is the one that's actually super important and really interesting, because here's an example from one of our users who has shared their data publicly. And you can see that here the person has like a lot of different symptoms over time, but the common section is the one that's the actually interesting one, because this person says like, well, every year I get the sinus infection that moves into my chest. And well, I do report having a lot of coughs these days, but actually I've been smoking more since I've been out of work. And if you would look at the other comments, you can see that actually being out of work is a symptom of the pandemic, because this person was laid off because of the pandemic and basically losing his job. And this actually led to reporting more symptoms, but it's certainly not having an infection right now. So All of this data, as I said, like a lot of it is already collected, and we can already do some first analysis, and we can see, even with just 6 data points, that we can see people that report falling sick indeed show that their body temperature rises before they're consciously aware. Their heart rate increases, at least for some of the wearables, if not in others. And as I said, we launched end of March, and we support the 5 most widely used wearables, at least of those that allow you to get access to the data. We have around 180 people that have joined and are actually logging their data every single day, and around half of them opt in into sharing. So if you are someone who's interested into exploring data, physiological data in relation to any infections, this is a really interesting and nice data set to play around with. And now, briefly talking about the impact that JOGL had on developing this project. So we started this, as I said, coming out of the Open Humans community itself. But we joined JOGL pretty much in the first week, I think, after we decided we wanted to do this project. And it has been super helpful, both in terms of getting a micro grant to actually finance some of the work, but also to just find volunteers to help working on this stuff. So for example, that we can use data from the Apple Watch is completely a volunteer effort. One developer on the Open COVID Slack of JOGL joined us basically and said like, oh, I know how to make this app. And then like less than a week, this person had completely developed this application. And then it took us, I think, 10 times as long to get it through the Apple App Store review. But like the development was really the least problem thanks to JOGL. Similarly, many of the other wearable devices were implemented partially or in total by volunteer efforts. And we had people that made all of these visualizations and did the preliminary data analysis, which was really great. So to just sum it up, as I know that we don't have a lot of time. So if you want to be involved, you can join our Slack channel. Everything that we do is open source. You can find the links to our code and all the data that's publicly available on quantifiedflu.org. And yeah, participate and share it with others. And that's it from our side. Thanks.
Thank you so much.